X or A naught, that B C naught?
A naught, B, C naught, yes.
A naught, B C naught. Okay. Alright, so actually get yourself into a little bit of trouble if you don't start with the correct simplification. So you got this B by yourself, that's where you should start looking. The term to the left and the term to the right, however, both have
A B.
B's.
Right.
So which one should we apply first? Well, I suppose in this case you want to apply the one that's the simplest to deal with. So if you apply the absorption version of exclusive OR here first, then you would have a B with an odd sign over 2 factors, so that it just seems a little more complicated. So I want to go here. A, B, XOR B is equal to what?
A naught, B.
Gotta pick the B without
the
the A.
Right.
A not B. Good. And then copy down everything else. XOR A not
B naught,
B,
B,
C not. Okay, simplify what remains.
Is it A naught, B naught? Oh, both the A naughts B, they're equal to 1, right?
Both the we have an A not B
on both
and an
sides.
A not B.
Right. So you have to choose that then? Is that
So yes, you have to choose the A without the C naught. Or
Right.
excuse me, you
The
have
A-
to choose
the
the
A
A
naught
naught
B
B
without
without
the
the
C
C naught.
naught,
So
right.
that would be A naught B C naught, which is C.
Oh, okay. That kind of makes sense.
Or another way to see this is the absorption does work for 2 variables because another way to see it is factoring. Exclusive OR you can distribute, therefore you can factor. That would leave me with 1 XOR
C.
C naught.
Right.
And
That's what I
then
had.
1 or XOR anything is the inverse of that value. So
C,
this
yeah.
would be A,
Not B times C.
same thing. So that absorption rule does work with multiple variable terms. Question. First page that you just couldn't seem to get. Excuse me. Page. There we go. Talked about 18. There's a bunch of different answers, and you can argue it's not simplified. We're going to take a different approach to something like 18 today. Any of these answers that have different timelines?
These make a little more sense.
review. Take your time.
Didn't do 17. That's on the previous page.
Get A, X, or B not. A not B. What should we do first?
We do De Morgan's law on the
De Morgan's law for exclusive OR. The weird thing about exclusive OR, it's the opposite of itself. So how do we apply De Morgan's law here?
and just say A naught XOR B.
A not X or B. Move over just one of them. A not X or B. Copy down the rest. X or A not X or
XOR B.
B.
Then
XOR's commutative and associative, so I can put together the relevant stuff, and in this problem, that would be those
XOR 0.
problems that are saying A naught, XOR A naught. Same with exclusive OR means 0. Same means 0.
Zero.
Therefore
So
0.
zero
XOR
XOR
0 is
0.
you'd get the same answer if you made the other choice. If you said A, X, or B naught, X, or A naught, X, or B. Because now when they're opposite, exclusive OR is equal to what? Opposite is 1. So you have 1 XOR. These are also opposite 1. 1 XOR 1 is 0. Let's actually try what we're going to be talking about today with number 18. XOR.
You did 18. You were doing it a different way now.
Yeah, so if you got 17 done, I'll take it.
You want the quiz too?
Thank you. Care about that. Yes. So unlike you normally do for me, put the quiz and homework
Yes,
in
that's
separate
right.
piles. Put your names on it. Wait 2 seconds.
Put your names in there. Put your name.
So the approach we're going to take today is instead of looking at this as a simplification problem, we're going to just eliminate the weird operation of exclusive. Get rid of exclusive. There's a couple reasons why we want to do this. We know a little bit more on how to simplify regular OR. We just spent more time studying it. We have a few more of the rules memorized. The biggest one, however, being your logic gates are still either and or, right? And those are your gates. Circuits are either series or parallel. There isn't just a simple exclusive OR gate. Exclusive OR gates are really made up of a combination of ands and ors. We talked about that maybe earlier this week, that an exclusive OR can be switched to A or B as long as you don't take the A and B choice, or that's the same as A without B or B without A. So when I first started going down the path of exclusive OR, I saw all of this, there's just a lack of definitive resources on the subject. So when I decided to go down this rabbit hole of exclusive OR, I was essentially making it up as I go along. I'm sure I'm not the first person that looked at all this stuff, but there isn't a lot of information out there. I was making students take an algebraic approach to applying exclusive OR, and it was really painful. Every exclusive OR, I made students apply this rule, and then we'd have these really long expressions that we'd go through and simplify. Until just a few semesters ago that a student suggested, well, why don't we put it into a truth table? Filling out a truth table for exclusive OR really isn't all that painful, right? We're looking for an even or odd number of ones. And then from a truth table, we know how to go from a truth table into a simplified Boolean expression through a Carnot map. I thought that was pretty smart. So first of all, this isn't probably the way we want to think about this problem in a truth table. Probably want to apply De Morgan's law for exclusive OR. So instead of having the A XOR B XOR C with a not over it, I want to apply De Morgan's law, put a not over arbitrarily just one of them. Fewer the nots. We also talked about how you could put it over any odd number. The fewer the nots, generally the better, especially if you're thinking about a truth table. So I just arbitrarily put it over A. We just have three variables, correct? A, B, C. Four, 2, 4, 2, 2, 2, 2. 1. We want to know A, B, XOR B, C, XOR C, XOR A not, XOR B. Let's just stick to that. I think maybe we could simplify that a little bit before we threw it in the truth table, but let's just jump in head first. All right. Each line, especially with these first few, maybe be a good idea to just write in what their values are equal to. So don't get myself confused. So let's first evaluate each one of these terms. So AB is only going to be equal to 1 when
Both are 1.
both are 1. So AB, that would happen here. Every other case, those are going to be zeros. XOR. BC, same thing. BC is going to be a 1 here, here, every other case, zeros. AC, same story. It's going to be a 1 here, 1 here, everywhere else is 0. And then A naught, when it's A is 0, we'll have a 1. When it's 1, we'll have zeros.
Top one, yeah, top four.
B, we just copy over 0, 0, 1, 1, 0, 0, 1, 1. C, same thing 0, 1, 0, 1, 0, 1, 0, 1. So I'm just filling out each individual term. Then to decide whether or not the statement is true or false with exclusive OR, what do we do?
Count the number of ones.
Count the number of ones.
Should be odd number of ones.
Looking for an odd number. If we have an odd number,
You got a one.
true. Even number,
False.
false. So 1, true, 2, false, 2, false, 1, 2, 3, 4, false. All zeros?
False.
False. 1, 2, false. 1, 2, false. 1, 2, 3, 4, 5, true. Once we get it into a truth table, we can take that truth table, put it into a Karnoff map. A naught, B naught, B naught, B, A, B, A, B naught, C naught, C. One more reason why I like this technique is because it fell at the end of the semester, which gave us an opportunity to review truth tables and Karnoff maps, right? All right, so how do I convert a truth table into a Karnoff map?
You just worry about the ones that are one.
Just where we have ones.
Yeah, everything else.
So where I have a 1 is 0, 0, 0. Where are my Karnoff maps?
A naught, B naught, C naught.
A naught, B naught, C naught. This top left corner.
Yeah, but what are the ones in the column in red there? What are they representing?
This is the answer to whether or not this is true or false. In green, those are just each individual term, whether they're true or false.
So how do you arrive at that based on the truth table? You just like,
You just
Well, A and
plug
B,
in- you
A
plug
and B
in
is
the-
only true when both A is 1 and B is 1. Because and requires both to be equal to 1. So it's true here and here, everywhere else was zeros. Same thing with B and C. And both have to be 1. So when B and C are 1, I have a 1. B and C are 1, I have a 1. Everything else is a 0. Okay? So I evaluated each of the individual terms, and then everything is an exclusive OR. And the way to evaluate whether or not an exclusive OR statement is true or false is, do you have an even or odd? So if I have an odd, it's true, even, false.
number of ones. That's what you're saying.
Not just the number of ones. Yep. Even number of ones are false, odd number of ones true. Right. All right, so the other place where we have a 1 is 1, 1, 1, 1, which is A, B,
A, B, C.
C.
So those are your two terms.
Yeah, those aren't next to each other,
Right.
so the best we can do
Simplification is
is that reading of the Karnoff map. Therefore,
A, B, C.
this whole
or
mess is equivalent to A,
A, not B,
B,
not C.
C, or we're reading from a Karnoff map. Karnoff maps are going to be or, not exclusive or.
Right.
A naught,
B, not C.
B naught, C naught. Okay. So we've eliminated the exclusive or. That is that simplifying? Well, sometimes it's simplifying, sometimes it's
Longer,
made
but it's-
much
yeah.
worse. This is just changing the form, not necessarily simplification. But that's what I'm asking you to do in this section. Change the form. Get rid of all exclusive ORs. And then simplify if possible, and we do that with a Karnoff map. But in this case, certainly, it appears like it is simplified.
So if we were to not do that and try to simplify it just without the Karnoff map and the truth table and tackle it? We would
So
still come
if
up-
I wanted to take an algebraic approach, I want to point out that you asked this question. I'm not making you do this, because this I used to make students do this, and it would be mutiny. So for example, let's just take one of our rules. Let's say A, X, or AB. So we already know the answer is
Right.
AB naught.
Right.
But if I wanted to apply an algebraic method for eliminating exclusive OR, the rule I would encourage students to use is this one. A, X, or B is equivalent to A, B naught, or A naught, B. Okay? What that means is, instead of A and B, you gotta think maybe left and right.
Right.
So there's the left side and there's the right side. So to apply this rule, that would be A, the left side, and not the right side, or not the left side and
And AB.
the right side. So there I have eliminated my exclusive OR. Now I'd want to go through and simplify.
Right.
And what would be my first step in order to simplify?
G Morgan.
I should apply to Morgan, so
Or
crack
A
that
naught,
open gives me A naught
or
or
B naught.
B naught. I need the parentheses.
Right, because you need to distribute the A there.
Distribute A. Well, here,
You can just knock off the A on the AB. Or no,
No,
it's
the
just
whole
zero.
thing.
It's
the
just
whole
zero.
thing becomes
Zero.
The whole thing is equal to 0.
So you have
And go through and
AB
distribute
naught,
A and A naught.
zero, or AB naught.
Not, I don't need to say 0, therefore
Right.
A, B naught.
Right.
It works okay in this case, but in general, all that algebra would typically frustrate students. So since I've moved to this method, maybe it's a little more work, but it's less frustrating for students to go through a truth table into a Karnoff map. Those techniques are probably more comfortable for students in general rather than algebraic techniques. So grab some examples from previous worksheets and apply this technique of eliminating the exclusive OR as opposed to just simplifying it in its current form. So this is coming from the problems we just worked. So this is number 7 from the homework you just turned in. B, X over B, X over A, dot B, C naught. It's actually, because going through a truth table and then into a Karnoff map is so much work, I would still, I guess, encourage you to try using the 2 basic rules that we had. So even an example like this, we have rules already that do get rid of exclusive OR, essentially. So we just worked this one a few minutes ago. So without applying this method, I could say that A, B naught, X or B naught is
B A naught or A
A naught, B without the A,
Right.
X
X
or,
A naught B C naught.
in which case that would simplify it down into A naught B without the C naught, therefore you get C. So I have removed the exclusive ORs by using the techniques that we currently have. Now, suppose you hate memorizing all these rules, or you just missed the fact that you could simplify this down. Going through truth tables into a Karnaugh map should give us the same answer. Let's give it a try. So, truth table first.
Yep.
A, B, C.
Easy not.
Evaluate each one of those terms for when they're equal to 1 versus 0. A, B is only equal to 1 when both are equal to 1, so that's 1's here, 0's everywhere else. B would be
one.
same pattern as B over here, 0, 0, 1, 1, 0, 0, 1, 1. And then when is A
When A not, B not is 0 and B is 1.
A not, A is 0, C
not
is
is 0,
0,
and
B
B
is 1. Only one place. 0, 1,
Third
0,
from the bottom.
right here.
Oh no, you're right. Third.
1, 2, everything else is going to be a 0. And then to evaluate the ultimate truth of the entire statement, so that's only the individual terms. Now we count if we have an even or odd number of terms.
0, 0, 0, 1, 0, 0, 0, 0. So only
Probably don't even need a Karnaugh map for
Right.
this, I guess.
only
Just a
A
single
not,
term.
B, C.
The only place where this is true is 0, 1, 1. Therefore, A naught,
B, C.
B, C. So, you could throw that into a Karnaugh map. It's just not necessary.
Very nice.
So yeah, this process of going through a truth table into a Karnaugh map into the simplified Boolean expression without exclusive OR is a lot of work, but some students find it far less frustrating than having to apply this technique. Let's take an example where we get a mixed bag. This is number 9 from the homework you just turned in. A X or A naught B, X or B C. Through simplifying, we could apply the common identity version
right.
of common identity in exclusive OR, which would knock out this A naught and change exclusive OR to regular OR.
Right. So A
But
or
we
B.
never fully got rid of exclusive OR. So the answer in the homework was A or B. I threw this problem on there to emphasize the point that you need parentheses here because you put those together first,
Right.
X or BC. And OR and exclusive OR have different orders, different levels to their order of operations. So you have to indicate that with a parenthesis. We were stuck, however, with exclusive OR. Can we I don't want to say simplify, not simplify, but what would happen if I just changed this into exclusive OR? If I have to choose between these two to apply this process, I'd just stay consistent and deal just with exclusive OR.
How'd you write it A plus B parentheses?
On the rule.
Because that's one of our rules for exclusive OR. So the rule for exclusive OR in the same scenario as common identities
Okay.
is you knock out that term but change exclusive OR to regular OR.
Okay, so yeah, the other one off was like isn't A X or A not just 1? So then that make it just like 1, just B.
Yeah, but we don't have AX or A naught. We have AX or A naught B.
Okay, because in the last problem we kind of like took one variable out like that. So I thought that was alright to do, but I guess not.
No, that's where we took that
If
one
it was the
variable
same-
out is applying
If they were
the
the same,
A.
but say for instance
XOR.
it was a A, B instead of A not B, you can say B, you have to choose the A, but not the B.
Yeah, you have to choose the A without the B, so you can only choose that one. Because if you choose this option, you necessarily have chosen both, in which case you fell into a trap. The A XOR A not B is, I've explained, as a loophole
Right.
that if you pick A naught's always going to be 0. So if you pick this one, this is 1, that's a 0. So no matter what you do with B, the statement is true. Therefore, this is the same as A or B. So it's the same as common identities except for you change exclusive OR to regular OR. But if the goal is slightly different, as you get on this homework assignment, eliminate the exclusive OR. So let's start with this. Write a truth table. Right? A, B, C. And on the homework, if you printed it off, I did give you truth tables and Karnaugh maps for each problem, so you don't have to waste time doing this on for each problem.
Zero, zero, one, one, zero, zero, one, one. Zero, zero, one, zero, zero.
You could do a truth table for the bottom expression.
I could. Yep, I could. But then I'd be thinking between regular OR and exclusive OR. But yeah, I could treat this the same way I treat the different factors. So I would just be doing OR rather than AND. So yes, absolutely. Both should give you the same truth table. And maybe we should just verify that, right?
Yeah.
It should say A or
B, X or BC.
C. Make sure those have the same truth table. So let's do that. First term,
Same, this is the left side.
same, right? So 0, 0, 0, 0, 1, 1, 1, 1. When is A not B true?
When A is 0, B is 1.
A is 0, B is 1. Here and here, everywhere else you're going to get zeros.
And only when
And
B and C is
BC,
1.
1, 1, here,
The bottom.
here, everywhere else. Zeros, then you count how many ones you have,
0.
except for, I suppose, 0 ones is 0 is technically an even number. Oh yeah, 0 is even, so
Right.
false, right? False, true,
false.
false,
True,
true,
true, true, false.
True. false, thank you.
False, yeah.
That's that one. Okay. Either form, if we're going to make the claim that these are equivalent to one another, should give us the same truth table.
Right.
Any way you change it, truth tables are kind of your universal checker. You can always make sure two things are equivalent by using a truth table. So we'd evaluate these two parts of my two sides of my exclusive OR separately. When is A or B true?
When either one is 1.
Either is 1. So really, when are they false in the first
When they're
two
both
cases,
zeros.
right?
Everything else should be 1.
And then exclusive OR BC is only true
When they're both 1.
both ones here, here, everywhere else. You should get zeros, and then count even or odd.
False.
Even ones, even ones, even ones,
One,
odd, 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 odd.
0.
No, I didn't get zero. Even number ones. Same truth table?
No.
What did I do wrong?
The fourth one down.
The third one down is not the same, and the fifth one down. So A plus
The fourth one down should be 1-1.
Should it?
Because it's the BC, both,
So I just didn't follow it over.
yeah.
Right.
I see, thank you. So that should be a 0, that should be a 1.
And then
That's both 1s.
Right.
So that's where it should be true. That's
Right.
We'll flip these
so
two
it should be
around.
1 0 then.
1, 0.
And
There.
now
They should
there's now they're saying
Now they are the same. Good.
Right. I was like, huh?
That would have been bad. Alright. So that checks out, but if I want it just in terms of ands and ors, now I can take any truth table, including ones that involve exclusive or, put it into a Karnaugh map. We only have 3 variables, A naught, B naught, A naught, B, A B,
A B not.
not.
C not C.
Let's see. Where do we have
A not B C not.
A naught B C naught A naught B C naught
A B not C not.
C naught
A B not C.
B naught C
A B C not.
naught
Yeah, we're good.
C.
Showing that 4, right?
1, 2, 3, 4. Get a 5th one.
On the last one, I think you did that.
ABC.
Yeah, ABC should not.
Oh,
Because it's false. It's false.
how many times have I done that now? I'm trying to make that true. 3 times now. Alright, I'll learn eventually.
So you should
And then what is the best way to read that Karnaugh map?
group them up.
Groups of
Twos.
how many?
3.
2 groups of 2.
Oh yeah.
This
done.
one.
So we got B C not and
A B.
A B not. Yeah. There we are.
So that would be the simplified way of writing it without an exclusive or. This would be the best way of writing it. Again, probably could make the argument that it got simpler than this, but probably not any simpler than this. I have my own internal theory that I haven't yet justified to myself that states that there's probably a way of writing any Boolean expression with just a single copy of each variable if you switch between all the many operations in logic, and or exclusive or may not be enough, but there's probably a way to represent every Boolean expression using just a single copy of each variable, but you probably have to incorporate all the different operations. But with 3 variables, might be able to get away with just ands and ors, exclusive ors. Try this again. Try representing this is number 11 from the homework assignment you just turned in. Try representing that in simplified as a simplified Boolean expression without exclusive or. Do I need to distribute this to put it into a truth table? not to put it into a truth table. I can evaluate this as a in a truth table in this form. Now, if these were regular ors, I could have put it into a Karnaugh map. Karnaugh maps require expanded form, but truth tables do not. In fact, I think it'd probably be easier to put it into a truth table in this form, because then I just need to figure out when is this 0, when is this 0. Every other case, it's going to be. So give that a try. Try putting it into a Karnaugh map in that form. Take that truth table. Excuse me. Don't put it into a Karnaugh map. Evaluate this as a truth table in its current form. Then take that truth table, put it into a Karnaugh map. Give that a try.
I thought an odd number of ones was true.
You still have to multiply.
Yeah. So what I'm doing here is actually ANDing. Yes, these in just a single column of greens, those are coming from odd versus even. Or with 2, it's same versus opposite. If they're the same, false, opposite, true. Odd number of ones, true. Even number of ones, false. Or even number of ones, false. So it's just these looking at A XOR B first, B XOR C separate, and then I'm ANDing those together.
Wouldn't 0 and 1 be 1?
0.
The second row?
We're talking about and in between these two. So and 0 is always 0.
Oh, we're not doing, okay, never mind.
No, the individual columns, those
Yeah.
are the exclusive order. We're doing those
Yeah,
first.
Yep, that
And
makes
then
sense.
you add them together.
A not B, C not, and A, B, not C.
Yeah, it should just be the two, right? They're
Right.
not next to each other.
A not B, C not,
Here,
and A, B not C.
Bottom right corner.
right corner.
Yep.
Agree? Yep, not next to each other.
Yeah, and they're not next to
That's
each other,
as
so
good as you can do.
there's only 2 terms here.
More simplified? Probably not. Really?
C.
Here we had 4 variables, 3 operators, the 2 exclusive orders, and an and. Only repeated B once. Here we repeat every single variable. We have a whole bunch of knots that are involved. So we have 1, 2, 3, 4, 5, 6, 7, 8 different operators. But in reality, you don't have gates that are technically exclusive or. They're a combination of and or gates. So this does mean the same thing. Mean the same thing. May or may not be, well, certainly doesn't appear algebraically to be any more simplified. If nothing else, it is a bit more complicated. Let's quick look at the homework assignment. I believe I have it posted, is that correct?
Yes.
So in each problem. Save you a little bit of time by printing the truth tables and Karnoff maps on the assignment for you. Certainly for these first couple that we're looking at, we don't have any rules that could simplify it any further. So we've used the truth table, the Karnoff map method. Although these next couple,
For number 4, did you need to have A or C and not A and B?
for number what?
4?
Four.
Not above
Oh,
it,
good
right?
catch.
Yeah.
Here.
Yeah.
Yes. So be consistent.
I mean, it'll be the same either way, but.
Change. Yeah, actually, I don't have this, so I should have this be. Thank you. Yeah, it's 2 variables either way.
Yeah.
But technically, if we've just done 2 variables, we'd call it A and B. So actually, this method that I'm suggesting would be a bit more complicated. Before you plug this into a truth table, there's a pretty simple way of simplifying this expression. What is it? Not 1, because it's or in between. So we actually got to apply the or rule for this.
Is it 1 to 1?
What's the or rule when the thing on the left is equal to the thing on the right?
It's just 1, isn't it?
For or.
1 or 0?
What's our rule? A or A
A.
is equal to A. Therefore, A, X, or B, or A, X, or B,
This would be.
you only need one of them. So it'd be the same as A, X, or B. So you'd save a little bit of time by not doing this. That's sort of a relatively new setup for me, so maybe I shouldn't put those in the truth table for you in case you want to simplify. But yeah, that would be the same as if you have a 0 here, you should have a 0 here. If you have a 1 here, you should have 1 here. And with regular OR, if they're both 0, it's 0. If they're both 1, it's 1. 4, now you're applying the redundancy rule for exclusive OR. The redundancy rule for exclusive OR is
0.
always 0, right? If they're the same, it's 0. So yeah, this is applying the redundancy rule for OR, redundancy rule for exclusive OR. So you should get 0 here. That would be obviously eliminating all of your exclusive ORs as well. So this method is less frustrating, but definitely in general could take more time. And they just grow as you go on. A lot of pages because I'm printing off, putting the truth table and Karnoff map on the paper for you in each problem, so it takes much paper, but it's not that many problems. But I would look for ways you could simplify the expression ahead of putting it into a Karnoff map and throwing it into a truth table. Certainly some of these, it's going to be much easier to simplify and eliminate those exclusive words. I want the simplified expression without exclusive ORs. That's what I mean by simplify and eliminate the exclusive ORs. Really, I want you to eliminate the exclusive OR and give me the simplified expression without that exclusive OR. All right? Give that a try. If nothing else, this method just plays out as a review of truth tables and Karnoff maps. Thank you.
Thank you.